Classical security relies on mathematical complexity. As quantum computers advance, the task of safeguarding global data shifts from solving hard math problems to applying the literal laws of physics, establishing security through nature rather than algorithms. Every classical optical network faces a harsh geographic reality. As light travels through silica fiber, it scatters and absorbs. This signal attenuation scales exponentially with distance, bleeding optical pulses dry over long intercity routes. In standard telecommunications, we solve this by placing amplifiers along the route to boost the signal, but in quantum networking, that is physically prohibited. The No-Cloning Theorem dictates that it is impossible to create an identical copy of an unknown quantum state. This maps the network's input layer constraints. Three mechanisms block long-distance transmission: photon loss, environmental decoherence, and the No-Cloning Theorem. These factors guarantee direct transmission fails beyond regional distances, as noise and loss overpower the signal. Securing long-haul infrastructure requires abandoning the amplify and forward model entirely. Instead, engineers must execute a complete architectural redesign, beginning at the exact point where the photon is generated. Most commercial quantum key distribution systems attempt to create single photons by taking standard lasers and heavily attenuating them, essentially dimming the light until only one photon should remain in a pulse. Legacy lasers follow a Poisson distribution. This means the laser inevitably misfires, emitting pulses with 2 or 3 photons. This enables the photon number splitting attack. An adversary intercepts a 2-photon pulse, splits one off to measure, and lets the second continue undetected. To counter this, network engineers must use decoy state protocols, injecting varying pulse intensities into the fiber just to monitor for these specific interception attempts. This adds significant operational complexity and reduces the overall key rate. Building sovereign infrastructure on probabilistic optical sources introduces a native security flaw. Resilient hardware must be deterministic by design. The required replacement for the probabilistic laser is the deterministic semiconductor quantum dot. This source is an indium arsenide and indium phosphide quantum dot embedded within a 2-dimensional photonic crystal. It functions as an artificial atom with discrete energy levels that allow for precise control. As shown in this schematic, by placing the structure within a micropillar optical cavity, engineers leverage the Purcell effect to increase the emission rate. When triggered, the hardware ejects a single isolated photon with no secondary particles. Recent studies by Jipeng Wang, Umair Abbas, and their teams measured the residual multi-photon probability for this setup at just 0.85%. This deterministic profile neutralizes the photon number splitting attack at the hardware level, removing the need for legacy decoy state monitoring. Single photon generation is only the first step. That state must then survive transmission through the vibrations and temperature swings of underground urban fiber. Traditional laboratory methods encode information using polarization, relying on the physical orientation of the light wave. Real-world fiber is subjected to mechanical stress and thermal shifts that induce birefringence, physically twisting the photon's orientation and scrambling the message before it reaches its destination. This distortion drives the quantum bit error rate past 11%, the theoretical limit where secure key distillation becomes mathematically impossible. Metropolitan networks cannot rely on these delicate spatial states. They require a qubit encoding methodology that is immune to physical fiber distortion. The resilient alternative is time bin encoding. Instead of looking at orientation, this method functions as a high-precision quantum stopwatch. Alice's transmitter uses a self-stabilized Sagnac interferometer. It splits the photon into a short path for a 0 state and a longer delayed path for a 1 state. Information is stored in relative arrival time rather than spatial orientation. This uses the principle of common mode rejection. Because environmental noise in the fiber stretches or compresses both time states equally, the relative gap between them remains intact. While Alice's setup is passively stabilized, the receiver at Bob's end uses an actively stabilized asymmetric Mach-Sender interferometer. This device uses a phase shifter and feedback loop to decode these temporal states. By shifting quantum information from the spatial domain into the temporal domain, the signal is hardened against real-world environmental noise. This architecture has demonstrated stable transmission over 120 kilometers of standard, non-specialized optical fiber. The system maintained a continuous link for 6 hours without requiring manual phase realignment, a significant milestone for unattended field deployment. The system maintained a quantum bit error rate of 6.85% in the Z basis, yielding a secure key rate of 15 bits per second. This was achieved by tuning the quantum dot's emission to exactly 1560.6 nanometers, the low attenuation sweet spot of the standard telecom C-band. These metrics prove the semiconductor quantum dot time bin system is a practical solution ready to co-propagate over existing global dark fiber networks. While 120 kilometers secures a metropolitan area, continental networks must surpass the absolute transmission limit of approximately 127 kilometers. This requires moving beyond point-to-point links and constructing segmented quantum repeater chains. This diagram outlines the repeater architecture. Panel 4 isolates the visible layer, the hardware stack, from the protocols running beneath it. Each repeater node requires specialized hardware, quantum dot interfaces, superconducting detectors, and complex cryogenic quantum memories to synchronize the states. While engineering this visible hardware, particularly the 4 Kelvin cryogenic cooling requirements, is a primary scaling bottleneck, the utility of the repeater depends on the protocol running beneath it. This graph represents the hidden layer, where quantum information is preserved without being copied. Solid lines show local entangled pairs bridging adjacent nodes. Through entanglement swapping, intermediate nodes perform measurements, destroying short links to forge an extended correlation connecting node A directly to node E. In a classical network, the signal physically travels the entire route. Here, the photon at node A never reaches node E. Instead, its quantum state is mapped across the destination through these correlations. This enforces continuity without duplication, achieving long-distance transmission while satisfying the strict constraints of the No-Cloning Theorem. This reliance on entanglement topology changes how we define a cryptographic key. Classical keys are static data objects stored in memory, which makes them vulnerable to being copied or eventually decrypted by more powerful computers. Panel 5 introduces cryptographic paraphrase, security derived from graph invariant properties. The key becomes an emergent property of the entire graph, existing only as relational correlation between nodes. This ensures meaning is preserved through transformation, not replication. Verification happens through the same syndrome checks and Bell state measurements used to maintain the repeater chain. Because the key is tied to the state of the graph, any attempt to observe or clone the signal collapses the distributed correlation, instantly alerting the network. A secure global network depends on this hardware-enforced reality. Duplicating a relational quantum state is a physical impossibility.